Hi, my name is Courtney Tanu, and my group mates Fernando Piedra, Trey Tatum, and I are presenting our numerical simulation of cryosurgery of breast cancer, a temperature distribution analysis. This is a roadmap that highlights a couple of points that we're going to touch during this presentation. First is the introduction, so we'll go over our purpose and a couple objectives we had for this project. Background, so you get a little bit more knowledge about cryosurgery. Modeling, results, discussion, and our conclusion and what we found out. Before we get started on talking about the project itself, our purpose was to gain an understanding on heat transfer and conduction through body tissues, namely tumors and breast tissue. A couple of objectives we had for this project were to model a cryosurgery procedure for breast cancer, to effectively simulate a real-world environment, and to compare data obtained from our simulation with data from that of peers. Before we get started with the modeling and simulation, we're going to have to ask, what is cryosurgery? Cryosurgery is the use of extremely cold temperatures, namely anything below -40 degrees Celsius, to kill unwanted tissues or cells. Cryoprobes are used in cryosurgery to send these really cold temperatures to kill the cells. In this simulation, the cryoprobe is set to -196. However, anything below -40 is fine. Ice balls form around the tip of the probe, and this temperature is then distributed throughout the tissue. Currently, cryosurgery is viable as a treatment for prostate cancer, but research is being done to support it as a treatment for breast cancer as well.
My name is Fernando Piedra. I was in charge of modeling, design, and simulation for this project. For this project, we considered two main tissues, the breast gland and the tumor. For the breast gland, we went with a hemisphere with a radius of 30 centimeters, and for the tumor, we went with a hemisphere of 2 centimeters. And finally, for the prop, we used a hollow hemisphere inside the tumor to represent the prop with a radius of 0.6 centimeters. Once the model got done, the next step was to create a mesh. In order to get accurate results, we create a mesh throughout all domains. Here in this picture, you can depict the 2 endpoints around the surface of the breast exposed to the environment. And then for all other surfaces, we choose a 30-point mesh. Next, for the tumor and prop interface, we create a mesh system consisting of 20 points between the tumor and gland interface, and 20 points between the tumor and prop interface. Around the edges of the tumor, we created a mesh of 10 points, as you can see in our PowerPoint slide. After the mesh was done, we went ahead and created some boundary conditions. On the surface of the gland, we set the temperature to be 37 degrees. This temperature was maintained constant throughout the gland. For the tumor, we set the temperature to be 37 degrees as well and maintained constant throughout the tumor. For the prop, we initialized the temperature at -196 degrees Celsius. Next, we created our materials. The materials that we researched were the gland tissue and the tumor tissue. This data was obtained from the NIH research lab. We did not research for the prop materials because we just set the prop to be 196 degrees, -196 degrees Celsius. Therefore, we didn't needed to look for properties of these. The were set up. We run the simulation. We run the simulation for 1,000 seconds with a step interval of 10 seconds. That way, we obtain 100 data points. The following is a video of what the simulation looks like. You can see that rapidly the cold temperatures are expanding throughout the tumor. For more information,
My name is Trey Tatum, and I will be going over the results, discussion, and conclusion of our numerical simulation. The probe initially was set at a -196 degrees Celsius. Cryoablation occurs at temperatures under -40 degrees Celsius, but we need to find a way to not harm the healthy tissue when trying to extract the tumorous tissue. as you can see, the negative 40 degrees Celsius cutoff happens at approximately 1.2 centimeters away from the probe. This isn't quite as big as the tumor, which happens to be about 1.5 centimeters in diameter, but it eliminates most of it. As you can see at the cutoff for what we did for the measurement of the tumor, which was 2 centimeters, the temperature is up to 13.5 degrees Celsius, which means that all of the healthy tissue up to and past that point will be unaffected by the temperature distribution. So the results of the ANSYS portion of our project are shown here. The global length of the healthy tissue was measured at 2.4 centimeters, but the minimum and maximum extent of it were 3 centimeters to ensure precision with our results. The density and thermal conductivity were kept constant for both tissues, but the main difference is found in the average diffusion time scale and the temperature range. The average diffusion time scale is much higher for the healthy tissue because it takes much longer for the temperature to change for the healthy tissue compared to the tumor, which has the probe in it. The temperature range for the tumor, however, is much higher than for the healthy tissue because of the bigger temperature difference in it. With the probe inside of the tumor will obviously have the highest difference in temperature because the healthy tissue is supposed to be unaffected by the temperature change, which is evident here. For cryoablation occurs up to temperatures of negative 40 degrees Celsius and below. With our simulation, we reach negative 40 degrees Celsius at approximately 1.2 centimeters away from the probe, which means that almost all of the tumor will be cut out. With the difference in temperature ranges, it is obvious that the tumor has a much higher temperature change throughout the process, while the rest of the tissue is somewhat unaffected compared to the rest. As I said before, most of the tumor was removed, about 80% of it, but 20% of the tumor is still left after. Main worries about cryoablation is the effect that it can have on healthy tissue, even while removing the tumorous tissue. It was found that most of the healthy tissue was unaffected outside of the radius of the tumor. The good thing about cryoablation is that even if you do not remove the entire tumor at once, you can perform cryoablation multiple times in succession without negative effects on the patient himself. Our data was consistent with Cha et al.'s results because their temperatures also reached negative 40 degrees at approximately 1.2 centimeters, and it reached 0 at approximately 1.8 as well. From our simulations, we conclude that cryosurgery will be a viable treatment for breast cancer very soon, but more research will need to be done to determine what temperatures the probe needs to be at for what size tumor. Here are the references we used, and they were used in this PowerPoint to compare our simulation results and to show that cryosurgery can be used multiple times in succession without hurting the patient. Thank you.